Hi everyone, in this video we will walk through how we built and evaluated our regression model for the medical insurance costs dataset. We will follow the order of our notebook and focus on two main questions: what we did to improve the performance of our regressor, and how we assessed whether the model was well fit.
We begin by loading the training dataset and examining its structure. The dataset contains 1,338 observations and 7 variables. The target variable is medical insurance charges, and the predictor include age, sex, MBI, number of children, smoking status, and region. After checking the dataset information, we confirm that there are no missing values, which allow us to focus directly on modeling rather than imputation. Then we load the test dataset separately, since this follows a couple-style setup where the primary objective is to minimize mean squared error on unseen data. This makes generalization performance more important than simply achieving low training error. Before modeling, we convert categorical variables into the numeric form. Sex is encoded as binary. Smoking status is encoded as yes or no. The region is treated as a categorical feature. To ensure consistent and reliable processing, we explicitly separate categorical and numerical variables and use a column transformer. Categorical variables are one-hot encoded, while numerical variables are passed through the unchanged. This pre-processing is implemented inside a pipeline. Using a pipeline ensures that the same transformations are applied during training, validation, cross-validation, and final prediction, which helps prevent data leakage and makes our evaluation more trustworthy. For the regression model, we choose the XGB Boost. This model is well suited for structured tabular data and can capture nonlinear relationships and feature interactions that simpler linear models may miss. To control model complexity and reduce overfitting risk, we tune key hyperparameters such as the number of estimators, learning rates, treat dips, and the subsampling rate. To evaluate model fit, we first split the data into training and validation sets. We train the model on the training data and compute the mean squared error on the validation state. The validation error is reasonably close to the training error, which suggests that the model is not simply memorizing the data. To further assess stability and the generalization, we perform 5-fold cross-validation. The cross-validated MSE is consistent with the validation MSE, indicating that the model performance is stable across different subsets of the data. Then, to further assess from the learning curve perspective, we can better understand how the model behaves as the training data size increases. As shown in the learning curve, the training error gradually increases while the validation error decreases and then stabilizes as more data is used. This pattern suggests that the model is not severely overfitting. If the model were overfitting, we would expect the training error to remain very low, while the validation error stays much higher and does not improve with more data. We also do not observe clear underfitting. Since the validation error decreases as training size increases and reaches a relatively stable level. Overall, the relatively small and stable gap between the training and the validation error indicates that the model generalized reasonably well. Finally, we retrain the model on the full training dataset and generate the predictions for the test set. These predictions are saved and submitted to Kaggle for leaderboard evaluation.
Overall, we improved model performance by using a strong nonlinear regressor, consistent pre-processing through pipelines, and carefully chosen hyperparameters. We assess the model fit using both a validation split and cross-validation to ensure stable and reliable performance on unseen data.